Okay, so I got this question in my email a couple of days ago. So let's go ahead and go through it. So the question is to, given this compound, label any asymmetric carbons R or S, and of course draw a star next to them. Draw any internal planes of symmetry. Label the structure chiral or achiral, and then label if it is meso or not, right? And really the first two sub objectives should have a little caveat to them. That is to say, label any asymmetric carbons. Of course, if they don't exist, or if there are no asymmetric carbons, then we can't label anything, right? Also, same thing with the plane of symmetry. If there is no plane of symmetry, we cannot draw it. Okay, so going through this compound, I guess let's go green, right? So I want to label any asymmetric carbons. Asymmetric carbons, we're going to restrict our definition to purely carbons that have 4 bonding areas, so sp3 hybridized carbons. And to make it asymmetric, we have to have 4 distinct groups attached to that carbon, right? So right away, if we look at this top carbon, right, so CH2, that's not applicable because this only has 3 groups, this carbon down here and then the 2 hydrogens. Likewise, so I'm going to go ahead and put a red mark. That would be helpful, right? So none there. Likewise, this carbon down here is also not okay. This carbon also not okay. This carbon also not okay, right? Doesn't have 4 groups. If we look at this carbon over here, we have 2 hydrogens on it, right? The 2 hydrogens are not distinct from each other, so that means this is not asymmetric. And likewise, if we look at this one, again, the 2 hydrogens are not distinct from one another, so this is, again, not asymmetric. I'm going to skip this middle one right here. If we look at this carbon, this CH3 and this CH3 that are attached to it are the same, right? Because they're both CH3 groups. So, whoops, I meant to get red. So that is not an asymmetric carbon. Likewise, each of the CH3s have 3 hydrogens. Hydrogens are not distinct from one another, so these are identical as well. Now, lastly, if we look at this carbon in the middle here, I'm going to clean up this structure real quick. Okay, so if we're looking at this carbon, we notice if we go this way on it, we have a CH2. If we go this way, we have a CH, right? CH2 does not equal CH. So those are distinct. Also notice that we do have a hydrogen in the back there to fulfill the octet. So it's not equal, right? Hydrogen is distinct from a carbon. And then likewise, this over here is also a CH, but this group is different from this group, right? It doesn't have to be just a thing that's directly connected to the carbon that is different. You could have 1, 2, 3, 4, 1, 2, 3, and 1, 2. That carbon would be asymmetric even though you have CH2, CH2, CH2 directly attached to it, right? What matters is that this whole chain is different from this whole chain, and that both of those are different from this whole chain. So if we look at this route over here, notice that this is squiggle and the rest of it, right? So this little squiggle is supposed to be like where this connects, right here. And if we look at this isopropyl group, it is squiggle like that, right? Clearly these two are not equivalent. So they're not equivalent, they are distinct, which means this carbon has 4 distinct groups, which means it is asymmetric or chiral. Okay, again, I'm going to clean this up and then we can continue to label it R or S. Okay, so here I've just drawn in the hydrogen that is implied by line angle notation. So we're going to start to label the priority groups on this. I'm going to use, what would come out best? Green, why not? Okay, so hydrogen is your 4th priority because it is the lightest. Right, we're deciding between a carbon, a carbon, a carbon, and a hydrogen. Hydrogen is the lightest. Now, for each of these carbons are all the same. Or, I shouldn't say they're the same. If we're just looking at the things that are directly connected to this, to our chiral carbon, we're stuck between a carbon, a carbon, and a carbon. We can't distinguish which one has a higher priority. So, we look at the things that are directly connected to these carbons and compare them. And just the atoms that are directly connected to it. Okay, so directly connected to the left carbon, I'm going to label that A, is another carbon, right, going upwards, and 2 hydrogens. I'm going to put that on the side, that little triplet. And important note, the triplet is an ordered triplet, right? It is ordered. Highest atomic weight atom first. Okay, so if we look, I'm going to change colors to make this easier to read. Okay, orange, call that B. Directly connected to this carbon is a hydrogen and a double bonded carbon. Now, we have to have a triplet of atoms to do our comparison. So what we're going to do is we're going to count the double bond twice. In other words, it's double bonded to a carbon, so we're going to call that 2 carbons. Right, and then the hydrogen. Oh, and of course, write that down over here. Ooh, carbon, hydrogen. Again, in order from highest to lowest atomic weight. Okay, and the last color, we'll go green again. Why not? Okay, now if we look at C, which is the other carbon directly connected to our chiral carbon, this has 2 carbons and a hydrogen. Carbon, carbon, hydrogen. So we'll write that down. Carbon, carbon, hydrogen. Now that we have our triplets, we will compare those directly. Our first atom first in our lists. Ooh, I can use a highlighter here. So comparing 3 carbons, they're all the same, so you can't make a decision there. Comparing hydrogen carbon to a carbon, hydrogen is definitely the lowest. So that gets our next lowest priority. That is to say, 3rd. And of course, hydrogens we can't make a decision on. So far we've been able to distinguish two of the 4 priority groups on our chiral carbon. So we have 2 pathways which we are following right now, which we haven't been able to distinguish yet. So if we follow this pathway, and if I do a different color, we've also been following down, right? we wrote out a triplet of atoms that were connected to those groups to try to distinguish, and so far that hasn't gave any fruit. So what we're going to do is we're going to go to the next carbon attached to them and compare those triplets. Right, so explicitly we need to compare that carbon to that carbon. And you'll notice here I went to the left to compare that methyl group. It wouldn't matter either way, because if I went to the left methyl or the right methyl, because the two methyl groups are identical. Again, label that something, give it a triplet. This is again double bonded to a carbon, although it is double bonding backwards to a carbon. Again, we still need a triplet to compare. So we're going to count carbon, carbon, hydrogen attached to it, right? So there's still C, C, H. Okay, and then if we go downwards to B, oh, this just has 3 hydrogens. Right, so from here, if we compare CCH to HHH, now that we have our triplets, we can compare them. We immediately notice that carbon is heavier than hydrogen. So then the yellow route gets our first priority because it is the heaviest. And the green route gets our second priority. Cool. Again, I'm going to clean this up. Lots of colors, lots of writing everywhere. But importantly, we have a priority group. Now we can go ahead and label this R or S. So at this point, we have evaluated our 4 distinct groups. We have labeled highest priority, lowest priority, and the middle priorities. Now we're going to actually be able to label this R or S. All right, we're going to connect 1 to 2 to 3. And the hydrogen is in the back, so we have the correct orientation here. We'll notice that this is steering to the right. Therefore, this chiral carbon should be R. Cool. Okay, so that's the first part of the question done. I'm going to clean this up again and then talk about internal plane symmetry. Okay, so after we've labeled the carbon R or S, we no longer need the priority groups. So I've erased all those. I've kept the star and the R. That's the important information from that. Now we need to label any internal planes of symmetry, and the first thing to note is that this only has 1 chiral carbon. So here's a couple of logical statement, right? So the plane of symmetry can go through the chiral carbon, or it can not. Right? So what we're going to do is we're going to suppose that we can draw a plane of symmetry, and then we're going to see if that leads to a contradiction or not, right? So we can split that up into 2 cases. The plane of symmetry can cut through the chiral carbon, or it can not cut through the chiral carbon, right? If it does not, whoops, right? If it does not, then one side of the plane of symmetry will have the chiral carbon, and the other one will not. Therefore, it is not a plane of symmetry. Right? Of the plane will have the star, the other will not, Therefore, it is not a plane of symmetry. Right, so just to kind of illustrate, so if we suppose this has a plane of symmetry, if this doesn't cut the chiral carbon, then the chiral carbon will be on one side. Right, it can only be on one side because since we only have one of them. So this will not have that carbon. Therefore, this is not a plane of symmetry because it doesn't cut it equally. Let me see if I can erase that. There we go. Likewise, if our plane of symmetry does cut through a chiral carbon, it also won't be a plane of symmetry, because if you take a chiral carbon a chiral carbon, rather by definition, doesn't have a plane of symmetry. So this also is a contradiction. Right. So what we've done here, is we have supposed there exists a plane of symmetry, and we've shown that no matter where we put the plane of symmetry, it won't be a plane of symmetry. Right. So no matter where the plane of symmetry is, it leads to a contradiction. Right. So therefore, we don't have any planes of symmetry. And actually, that's true in general. If you only have one chiral carbon, you don't have a plane of symmetry. Right, so that's the second part done, right? Third part, label a structure chiral or achiral. Kind of following through with the definition here, are an equivalent form of the definition of chiral or achiral. If we'll call this A, whatever, some compound has a plane of symmetry, then A is achiral. Right? So from our discussion in part B, our compound does not have a plane of symmetry, therefore it is chiral. It is not achiral, it's chiral. Right? So it is chiral. And an important note for mesostructures, meso by definition is a achiral structure that contain chiral centers. And achiral structures that contain chiral centers. So again, our compound is not achiral, so it also cannot be meso. Some examples of meso structures would be like the human body, for example. Right, we have a right hand and a left hand, and right down the middle is a plane of symmetry. Right, so we have chiral centers, that is our hands, but we still have a plane of symmetry, so we are achiral as a whole. Okay, so let me know if that helped, or if you have any more questions, go ahead and post them in the comments and whatnot, or just send me another email. And I'll see you on Tuesday. Yeah.